thanks, Daniel, for organizing this. It's really an absolute pleasure to be taking part in this special day. I'm currently I was invited to a workshop in Denmark on black hole mergers, so it's a bit hard to say no to an invited workshop at my career stage. But nevertheless, I still feel quite sad, but by not being there in person. Just for example, I think I'm missing this event and some friends' wedding next week. I'm okay with the wedding, but I kind of got over it. But missing this is still a bit hard on me. But yeah, anyway, I'll be just taking the time to reflect about my own work and how the driving the main themes of both mine and Rosemary's principles were also driving my work, and a bit of lookout on the future as well. So one concept that Rosemary likes, and I, myself as well, is the idea that beauty should be simple. I really, I was looking for pictures and I found this one, and I found this quite tranquil, and it makes me quite relaxed. What did not make me relaxed initially, it was my first PhD project where we were trying to explain the stability limit of various stuff in the solar system, and the idea here is that, sorry, you have a free body problem, you have the sun in the center, you have a planet, and you have some moon. So these free bodies are in a hierarchical configuration. But besides the famous moons that we have now, we also have a lot of smaller moons, at least for the giant planets, and they're quite numerous. They're also located further away from the regular ones, and they also have to be much smaller, and their orbits are also much more erratic in the sense. They tend to have relatively high inclination angles, where the inclination angle, by that I mean just the relative angle between the plane of the orbit of the satellite with respect to the orbital plane around the sun, and this is the angle here. And you can always describe the orbit also with various other orbital elements, various angles. So these orbits tend to have very inclined orbits, and also they tend to be quite eccentric. And in addition, you see that most of them are actually retrograde, meaning that their inclination is above 90 degrees, so they counter-rotate in some sense. And you also have this cavity that you don't have the satellites at all. So it took me some time to kind of like get through it and digest everything. And eventually we had a fancy high-order perturbation theory that really explained these observations. Normally, I don't show these equations, but I have allowed myself to do it for this talk, especially for Rosemary. And what happens here is that, we basically can predict what could be the maximal eccentricity of these orbits, and we can, based on some fancy mathematics, and eventually if we get this to clustering here. So this ellipse and this one, and they see, if you squint a bit, they tend to correspond with the areas here of relatively relaxed parameter space, at least in inclination versus separation, and it seems to be fit well with the observations. So, I was happy. It was my first paper from the PhD, and in the first day it appeared on the archive. We got an email from Rosemary that basically told us that we did not cite the right paper, and we also needed to correct some things, which we did, and that was almost 8 years ago. And at that point, I was a young student, so I felt to me like, like Zeus himself descended from the heavens and actually took time to read my obscure paper. So that was a fun experience, and I think since then I got into this resonant condition on keep working on this stuff, and also keep trying to seek Rosemary's attention over the years. And indeed, to this day, I think hopefully I have improved, but I've actually learned that I should try and simplify things and not make them more complicated. Although we all tend to do it, but I think it's good to try sometimes find nice patterns. For example, we can think of the complex evolution of hierarchical free body systems, like for these triple stars or whatever. It's now today we know it's really almost the same as a pendulum in some sense. And why do we think it's the case? It's because If you look on the Hamiltonian of the pendulum, you're going to have something that is quadratic, which is the action or the momentum that we have. It tells us how much initial energy we could get. And we also have something which is plays the role of the angle. So for the pendulum, it is the actual angle. And really have something similar here also for this fancy Hamiltonian. We have something which is quadratic in something that plays the role of the action or the momentum. And we have something that's actually a constant of motion. So ignore that. And we also have something that really plays the role of the angle in some sense. And if you remember trigonometry, cosine is roughly the square of the sine of the half angle, so it's kind of the same thing. So I was happy that we could draw these analogies eventually. And even to this day, I'm actually still working on trying to make complicated Hamiltonians into relatively simple figures, where basically the phase portrait for this Hamiltonian is essentially this thing, where you have constant curves and you try to test within body to see if it's good or not, and it's not so bad, I think. So actually, as you can see, my first work on these things was almost 8 years ago, and this paper was actually last week, so it's a nice closure to some extent. And basically, yes, so this face portrait is really very much similar to what you would expect from from the face portrait of a pendulum, because you have all the features of a fixed point, of closed librating orbits, of separatrix, and open curves of circulating orbits. And in addition, I still sometimes think of the negro satellites, and this is the other paper I wrote on this topic. And the point here is that there are many details here, and it looks complicated, but really the takeaway message here is these two things. Because if you try and to explain the motion of the satellite that has some parameters, if you try the naive version, it doesn't really work. You need to add some other perturbation layer, and then you get this fixed point and the separatrix, and it's not super accurate, but I think it works much better than to try something naive. So I think just boiling down a problem which is complicated into something as simple as, okay, do we have a fixed point or not? I do think it's a nice simplification and really in line with the with our philosophy of trying to find simplicity. And the other thing is that of interactions are obviously chaotic, and we know that we probably heard during the entire day. Well, it was night for me, but for some of you it was day. That really things are chaotic, and chaotic patterns appear and fractals appear everywhere in nature on various scales, from snowflakes to planets, and more than that. And really, the other kind of interactions with Rosemary were also chaotically scattered spatially and also both temporally. So I think there was some spiritual interaction, at least in the first triple conference that my supervisor organized in Haifa. And we actually were able to meet in person 2 more times in Europe in 2018 and 19. And since I moved to Australia, I think it's became a bit more much more close encounters, but I could not find that typical frequency for this thing. So I think if I do the power spectrum, it will be also chaotic probably. And soon we will also have another encounter, this time in Europe, in Prato. So next month, which we're gonna have some nice week talking about free body and chaos and all the stuff that we like to do. So I'm really looking forward to it, to see Rosemary in person. So yeah, it should be fun. Anyway, so chaos, yes. So I think the other thing that really drives, again, with the simplicity and our passion, is really trying to take things which are complicated, even if they're chaotic, and try to get the essence of them. So I was actually awake for Rosemary's talk, so I can prove this because I know that she mentioned the double pendulum, and indeed you see here that yeah, if you just take two masses and two lengths, if you have the right parameters, you cannot really predict what's going on, and eventually the this tracer it will look also chaotic. And the idea is that if you have a system where you have two typical frequencies, let's say if one of the rods was much longer than the other one, then the frequencies would be different. So maybe one resonance would be lying here in some resonant angle, and the other one was here, and they did not talk to each other, and everything was fine. You can basically decouple one one pendulum from the other, but in this case the frequencies are commensurable, so you really have this overlap criteria that basically the both separatrices of the of the typical frequencies touch. And if you have something in the system, you can't really know which frequency to follow, and you're getting up, you're ending up with this chaotic evolution. And this criteria is actually dates back all the way to Chirikov in the late 70s, and it's really used widely, not only in astronomy, but I think everywhere. You probably heard a lot of these things already. And indeed, at least for astronomy, at least this paper was trying to, how do I move forward? Yes. This paper was trying to model the evolution of a stellar spin, which is driven by a planetary orbit which is also varying in a triple system. But also, you can do something equal. You can also think of quadruple systems, in the sense that you have this nested binaries, 3+1 binary. So you have some inner one, maybe Earth and Moon, maybe you have some other star, and maybe some outer companion, and you have three angular momentum vectors. You do have two typical secular frequencies, which is basically how fast orbit A does things, rotates around LB, and how fast the intermediate orbit rotates around C. And whenever these frequencies are comparable, you will get a chaotic evolution. At least here they will have some example on some typical timescales of the evolution of the orbital elements of the inner binary, which is in the blue lines. So this is from a paper a few years ago also. And we can do this experiment many times and have many initial conditions and basically record, vary some small parameter and try to record. In this case, in this case of Storchan line, it was the misalignment angle between the stellar spin and and the planetary orbit in the last 500 iterations or whatever. And here it's a variant of that. It's a 2D plot of some other parameter that measures how how much extra-apsidal advance is important versus some parameter that also measures the ratio between two timescales. But in this case, instead of the spin of the star, we measure the misalignment of the moon, of the orbit of the moon versus the orbit of the planet. And although it seems like it's a different problem, the behavior looks really the same, because here we have nothing, it's almost zero, which is the blue lines here. You have some small excitations here, which corresponds to these stripes, and eventually at some point all hell breaks loose, but you do have some mixing eventually. So I thought it's kind of nice that you can take these complex things and boil down to relatively simplified principles. And the other thing, which is again very similar, it's something that's called a system that if you have a wide triple, let's say that your outer orbit is roughly 10 to the 4U, maybe more, then you could feel the tidal perturbation of the galactic field, for example. If it's, we are in a disk galaxy, so we can model this as a perturbation of some external driving. And indeed, you have these, so that orbit goes, does this eccentricity evolution, which are quite regular, but the inner orbit basically goes haywire and behaves in a weird way. And again, you can do this many times, and the picture you'll get, as a function of some initial ratio between secular timescales and the tidal timescales, you do get these like standard cases where only the polar orbits do something interesting and become eccentric. But once our frequencies becoming comparable, a window of opportunities is opening up, and we do have a sea of chaotic encounters and close encounters and mergers and etc. And you can map them to to different star evolutionary tracks, and you get like a lot of options for interactions of binary stars on various evolutionary stages, and that opens door to a lot of astrophysics, basically, that I don't have time to talk about. So that's fun. I think the last thing that I think was mentioned or should be mentioned is really testing assumptions and being careful about what people assume, and really expect, maybe try to revise them and maybe expect something unexpected. For example, I was lying to you here because this thing is incorrect, and it is incorrect because you have this double averaging in this sense, but really, when you do the first averaging over the moon orbit, the Earth advances by roughly 1/12 of the angle, because the period ratio is 1/12. Therefore, you need to have some extra corrections, which are a bit complex, but you can do it. And if you try to have a sector of here which is in the red lines versus the n-body, you do have deviations, and at some point, if you play with your parameters again, you really can't really predict anything, and you have to be a bit more careful. And we found a way to do it, and we actually have some nice predictions. So I did this paper in my PhD. At least, yeah, we basically derived the green line over here, which is the corrected version if you want to calculate maximal eccentricity of a triple system. And we ran some simulations, and it fit really well. We also find actually where this is not valid, and we can get anything. So the
time, Evgeny.
eccentricity is unconstrained. I know. Sorry.
It's time.
Yeah, give me 30 seconds, and I'll be done. Thank you. And also we have the same for non-testable limits. So that's a paper I did with a student here. And finally, that's my last slide. Actually, we applied it to where basically two stuff in the capable were colliding. It could get you fancy papers in fancy journals, but it's really the same principles that you have some breakdown of some assumptions, and that could open windows to new things. So yeah, just to summarize, resonance scales appear really in many astrophysical contexts, and we should really check the assumptions. But I think on a personal level, people like planets come and go, and most don't stay nearby for that long. But sometimes people are captured into something else called friendship resonance. And no matter when we see them or how far apart, I think we know that this another encounters between friends should be guaranteed. And I'm positive that we will do it with Rosemary many times. So thank you for listening.